In this video, we're going to discuss the closure of a set in a topological space. So if A is a subset of a topological space x tau, then a point x in the set X is a limit point of A if every open set containing X contains a point of A other than X. So if every open set U containing X contains some point A other than X of A. So for all U open such that X is an element of U, there exists some A in A minus the point X, some point other than X itself, that is both an element of A and in the set U. So here's a new definition. If A is a subset of a topological space x tau, then the closure of A is the union of A with its limit points. And the limit points of A, as we saw before, are denoted A prime. So A closure is the union of A with its limit points. So it's a set that contains A. And this is A closure equals A union A prime. So this is actually the same definition that we had when we discussed the closure of a set in a metric space. So both of these definitions are the same as we had for metric spaces. So when we consider the following theorem, a lot of this is statements that we've proved before. So using these same definitions, we proved that A closure is the intersection of all closed sets containing A, and therefore A closure is the smallest closed set that contains A. We also proved that a set A is closed if and only if it's equal to its own closure. We proved that A is a subset of B implies that the limit points of A are also limit points of B, and therefore A closure must be a subset of B closure. So all of these we've proved previously in the context of metric spaces, and therefore these proofs do carry over since we're using the same definitions. One last statement we haven't proved yet is 4, that the closure of A union B is equal to A closure union with B closure. So let's now prove this. We're going to use each of the parts above, parts 1, 2, and 3 of this theorem when we think about the proof of part 4. To show that these two sets are equal, we'll show that each set contains the other. For the first inclusion, first we know by 1 that the closure of a set is the intersection of all closed sets containing A union B. So if we can show that A closure union B closure is closed and contains A union B, then it must also contain A closure. So we know that A closure and B closure are both closed by part 2 above, that a set is closed if and only if it's equal to its own closure. So clearly the closure is a closed set. And so that means that A closure union B closure, a finite union of closed sets, is also closed. And we also know that, of course, A is a subset of A closure, B is a subset of B closure, so A union B is a subset of A closure union B closure. So then by 1 now, since A closure union B closure contains A union B, that means that A union B closure is a subset of A closure union B closure. Now for the reverse inclusion, we see that we know that A is a subset of A union B, and B is also, of course, a subset of A union B. So by part 3 of the theorem above, if one subset is a subset of another, the closure of the first set is a subset of the closure of the second. So A closure is a subset of A union B closure, and B closure is a subset of A union B closure. So what do we have then? We have then that, therefore, since they are both subsets of A union B closure, that means that A closure union B closure is a subset of A union B closure. And we're done. Note, we said that this is true about unions for closures of sets, but in general it is not true about intersections. So to see that this is the case, let's look at a counter example. Let's consider the real numbers with the usual topology. In other words, the topology induced by the usual metric on R. So that gives us open intervals as the open sets, and any union of open intervals is an open set in R with the usual topology. So let's look at the set A equals the open interval from 0 to 2, B is the open interval from 2 to 4. And then we'll compare A intersected with B closure with A closure intersected with B closure. So A intersected with B closure, that's, there's no elements that are in common with A and B, so that's the closure of the empty set, and there are no limit points for that empty set, so it's just the empty set. Whereas A closure is the closed interval from 0 to 2 in the real numbers with the usual topology. B closure is the closed interval from 2 to 4. And so the intersection of these two sets contains the element 2. And so we see that these two sets are not equal in this example. So in general, it is not the case that the closure of the intersection is equal to the intersection of the closures.